Hello. In previous videos, we were focused on definition of function, some very simple functions that solve some simple problems, and last part was about lists. So unlike in programming languages like C# and so on, in Haskell, the basic data structure that we'll be using in our programs is a list. So these things were covered. In this video, we will talk about type classes. It will be just so short introduction because we will be using them. Then we will talk in more details about functions. Uh, Functions are first class values in Haskell, so functions can be used like parameters. A function can return a function and so on. So we will somehow revisit the definition of the function that was mentioned before. So it's slightly more complex if we consider these things. And finally, at the end, I will show you some example how to do, let's say, some more complex function and how to use construct like let in and so on. So first of all, we were already speaking about type classes. In our example, we had something like a function f(x, y), and what we have done, we have add these two numbers together, and if we make the system, this Glasgow Haskell interpreter, to interfere the type of such function, the definition will consist of some type class. So the basic idea, we already spoke about it, the basic idea is that this function takes some types. There are two operators, two values, and some sort of result. And this type A, this type variable A, represents some type, but it's not any type. In fact, because we are using operation plus, then we cannot use this operation plus with any type, but we can use only it. We can use it only with some numbers by default. So this type class num represents all numbers. A different example of the same can be a function lm. We can take this built-in function that's a part of the module Prode, and this function takes some foldable structure. We will talk about it later, and more importantly, we have written our function is element in laboratories. So if we want to check if an element is a part of some, let's say, some list, we need to compare two elements, and this comparison is not a given. We must provide a way how our types are compared, and this is the example that uses the type class equality. So how a type class is defined in Haskell? Here on this slide you can see some examples. So there is a keyword class, but it's not related to types like in programming languages like C#, Java, C++, where by defining a new class you are defining a new type. Here it's related to type classes. So using the keyword class, we are able to define a new type class. Then we can add our types into these defined type classes. What is a type class? From the name you can see that it's some package, or it's some we have combined together some types, and the critical part is that we have defined some operations, and all these types that became member of this class needs to provide these operations. We need to implement these functions or operators for them. In our example, you can see that there is a class equ defined for some type A, and for this type A we need to provide two operations. In this case, this operand for equal and operand or operator for not equal. And if we want to have if we have built a new type, for example some car or color or something, then we need to provide the implementation for these operators, and then our type can be a member, can become a member of this type class. Moreover, these operations can have some relations between each other. So in this case, if we provide the equal operator, then in fact we have provided also not equal operator, because we can use just the function not, as is mentioned in this example, and we have the opposite operation. So because there can be some relations like that, we need to provide the smallest set that provides or implements all the other operations. So this is a basic idea about what a type class is, how they are defined. Later we will try to define our own types, and we will add them to some type classes. So we already know about type class equ. It integrates all data types that can be compared using these equal or not equal operators. There are also other very useful type classes like port, if you want to compare values, if one value is smaller than the other and so on. What we are really using when we get the result printed on the screen, in fact we are using a type class show. It has one function show that transform any value to a string, and this string can be, for example, printed on screen. So later, if we will be building our data types and new data types, usually one of the first things that we need to do is to add this type into a type class show, so the result value of this data type can be written on screen or printed on screen. Opposite class to show is read. If we want to read a value from keyboard, then it has a method read that transforms the string into the value. So these are some basic data. These are some basic type classes that will be used in our examples. In most our examples or in most functions that we will be implementing, we will be using only simple or basic data types like integer, double, string, and so on. And all these operations like equal, not equal, show, and so on, they are already defined for these basic data types. But later, when we will be creating our own data types, we need to be careful, and we need to know about these type classes, because then these restrictions that are in fact placed on our functions that find some maximum in a list and so on, then they become important. The most important part of this video is some information about function as a first-class citizen in Haskell. So before we spoke about functions types. In our example of function f, we said that the first value here, the a, is first parameter x, then the second one is second parameter epsilon, and the result will be the last part, but it's not really true, or it's true just in some cases. So let's say that, for example, our function will have a function definition, function types definition like that. So right now it has 4 values. So is it even possible? Is it okay? In fact, this arrow can be viewed like an operator with left-hand associativity. So to, let's say, fully understand the meaning, we can put all the parentheses in the definition. So in fact, we can add them like this. So right now, maybe it provides a better view on the type definition. Now the first A is parameter x. What remains if we apply, if we perform this functions application for the x, what remains is a function that takes one argument and returns the last part. So if we provide second argument, this second a, then or second a, and we replace it on epsilon, that what remains is all this. So from this perspective right now, from the type definition, we can see that such function takes 2 arguments, 2 types represented by this type variable a, and what it returns, it's a function. So right now we have a function that returns a function. Of course, here the implementation is wrong right now. So what we can do, we can, for example, say, okay, so here we add these values together, and we will use, for example, a plus with this value. So right now it's correct. So here you can see that functions can return another functions. How do we understand this expression? So first of all, if we have a plus, we can use it like a function. We already spoke about it before on laboratories and so on. So if we write something like plus is in parentheses and provide 2 values, then we have we can use it like a function. From the previous part, you can see that the function is able to return a function. So if we use the function f, if I reload the file and use the function f and provide 2 values, then in fact what it returns is a function. And here you can see that you cannot really write a function on screen. But because it's a function, then I can add a new parameter, and then I get the result. So here I have created a new function. The type is this, and then if I provide a value, then I get the result. So in this case, it adds these 2 values together, and it's a first parameter for the next plus operation. So what you can see is a function can return another function. Moreover, I can use, here we can see first part, first important information about functions. So a function can return another function. Second part is about partially applied function. So this type definition, let's say, is very important. It has some sort of insight how these data are evaluated. So if we if we give the first parameter into our definition, that what remains is the result of this operation. and we can use it. If the previous function was able to work, the return value was some sort of function, then even the intermediate result is a working object, and I can use it, and I can use this function. This function is called partially evaluated function, because we have not provided all parameters but just some. So the same as before also works. We already have seen that if we have this plus, so I can provide just one operator, and the result is again a function, and I can use it, so I can add new parameter. So if we have a function, we don't need to provide all parameters, but still we can work with the function. So if we provide just some parameters, we have partially evaluated function. So here we have a function that adds 1 to the second parameter, and we can work with that like with a function. So we already know that there are partially evaluated functions. We already know that a function can return a function, and finally we can also use a function like a parameter. So in our example, we have, or in this presentation, there was an example function applied twice that takes a function. So let's say we first write this function and some parameter, and applies this function twice on this parameter. So something like that. If we store it and reload it, then we can call this function apply twice. Let's say we have a function +1 as before. So this is just a shortcut to the previous expression. In fact, also the ordering in which I put these elements is important, not for plus because it's a commutative operation, but for other operations it can be important. Here it's x plus 1, in fact. So we have this function, and then we can provide some parameter, let's say 1 again, and the result is 3. We have applied this function +1 twice on the given parameter. So you can see that we are able to work with a function. Function can be a parameter to another function, and so on. How do I recognize this situation in types definition? If we get the type interfered by the Glasgow-Haskell interpreter, we can see that the whole first part is in parentheses. Now we cannot remove them. So in fact, this whole expression is the type for the first parameter. So we can see that the first parameter is a function, and we can work with this function. So this is some example of a very simple function that use another function like a parameter. Usually such functions are called high order functions. Maybe this example is not that important, or it's not the best example because its value is, let's say, or its usefulness is limited. But a very useful function that is frequently used in real programs is a functional map. This function takes some function and a list and applies this function on each element from the list. So let's say that we have again a function +1 and a list 1, 2, 3. So the result will be a list 2, 3, 4. We have applied the function +1 on each element on this list. So this is some sort of conclusion to functions. In our previous videos, it was, let's say, somehow restricted to these simple cases, but right now you should know that a function can return a function like a result, or its parameters can be also some functions. Moreover, we can have we can use some technique that is usually called something like a point-free programming. If you consider the function compare with 100 from the example, it uses the function compare. So if we search for the function compare, it's a very simple function that takes two values and compares them. If we compare 1 and 2, then we get the ordering is some sort of enum, that enumeration that takes that has three values, smaller, bigger, or equal. So now you can see that the 1 is smaller than 2. If I swap them, then it's greater, and finally, if I have two values, so they are equal. So let's say that we have a function like that. As before, if I provide just one parameter, so the result is a partially evaluated function that compares everything with 2. So I can use it like that. And finally, what you can see in this example is if we want to implement a function that compares everything with value 100, so the first option is that we have used before is in this command. So we can have a function with one parameter x, and then compare this x using the function compare with 100. But valid is also the second variant of this function. So the second function has no parameters, and in fact what it returns is a function. So it's the same like if we put parentheses in our examples. So this a arrow ordering is the result. This whole expression is the result of the function. So the function compare with 100 as it is implemented on this slide is in fact a constant function that returns another function, and then because it's a function we can use it like a function. So it will work nearly the same as the function in the command, or it will be the same function, but maybe if we remove these unnecessary parameters, it's more readable. So this is, let's say, a preferred way how to implement such function in Haskell. So this was some theory about functions definition. We have revisited what we said before. So now you should know more about the functions definition, about its type, and the possibilities how to work with functions.